In this video, we're going to look at oxidation reductions, how you can tell when an oxidation reduction reaction has occurred. We'll track the electron transfer and we'll count the number of electrons transferred. Let's start with the basic definitions. Oxidation is loss of electrons. So when a reactant loses one or more electrons, we say that that reactant's been oxidized. At the same time, because it's causing the other reactant to be reduced, we'll define that reactant as the reducing agent. Another sign of oxidation is when a reactant gains oxygen atoms. That is, the number of oxygen atoms bonded to that reactant increases on going from product to reactant. And a less common occurrence in general chemistry, but one you'll see in organic chemistry, is when a reactant loses hydrogen atoms. That will be a sign of oxidation as well. Let's look at reduction. Reduction is really the opposite. Reduction occurs when a reactant gains one or more electrons. When that happens, since it causes the other reactant to lose electrons, we say that a reduced reactant is the oxidizing agent or the oxidizer. At the same time, evidence of reduction is that a reactant loses oxygen atoms, meaning it's bonded to fewer oxygen atoms on the product side than on the reactant side. And again, one we won't encounter in general chemistry, but you will in organic chemistry. When a reactant gains hydrogen atoms will be evidence of reduction. Let's look then at oxidation number. That's the method that we're going to use to track when electron counts have changed and to determine how many electrons were lost or gained. So the first rule in finding an oxidation number for a species is if it's an element. In that case, an element is going to have a charge of 0. It doesn't matter how the element occurs, whether it's a metal like aluminum or whether it's a molecular species like phosphorus, then that is going to be an example of oxidation number of 0 for an element. If we have an atomic ion, meaning an ion that just consists of a single atom, like Mg2+, zinc 2+, Cl-. In those cases, it'll be simple as well, that the oxidation number will just equal the charge. Now, when things become more difficult, for example, in polyatomic ions or compounds, molecular compounds, we're going to make things a little easier by assigning two oxidation numbers that will just keep constant. Now, one of these is oxygen. Whenever we encounter it in general chemistry, we'll say the oxidation number of oxygen is going to be a -2. An example is in the permanganate ion, MnO4-. We'll assign oxidation number -2 in that species. Same in chromate, CrO4-2-. Hydrogen, whenever we encounter it, we'll give it an oxidation number of +1, like in water. So does that mean oxygen has a charge of -2 or hydrogen has a charge of +1? Not necessarily. In fact, most of the time it won't mean that. But again, oxidation number need not be the same as charge. It's just a counting tool. Then we'll have one additional rule. If we encounter molecular compounds, then the sum of all the oxidation numbers, the atoms that are present, must add up to 0. For example, if we encounter H2O liquid or SO3 gas, all the oxidation numbers that are present for those two molecular species must add up to 0. And finally, if we have a polyatomic ion, the sum of the oxidation numbers would have to add up to the charge. So in the permanganate ion, MnO4-, all the oxidation numbers must add up to -1, since that polyatomic ion has an overall charge of -1. And then chromate, CrO4-2-, all the oxidation numbers would add up to -2 in that case. Okay, let's look at an example of how we would find an oxidation number or when this would be important. Well, let's just get our rules here, the ones we just reviewed on the previous page. So we'll set those up here as a list. And then let's look at how we would find the oxidation number of the manganese atom in the MnO4-. So in other words, we're going to focus on what the oxidation number of manganese is when it's present in this overall polyatomic ion MnO4 minus. So we'll start by assuming that the manganese oxidation number is X. We'll just assign that its value in algebra is an unknown. We already know the value for oxygen, so each oxygen atom is -2. There's 4 of them. So the contribution from oxygen in the permanganate ion is -8. And the overall total charge, because the permanganate ion has a charge of -1, X plus the -8 has to add up together to be -1. So we can make a simple algebraic equation out of this. Manganese 8X minus the 8 from oxygen has to equal -1. Solve that for X. And we find that X, which is the oxidation number of manganese, is +7. Now, does that mean manganese has a charge of +7? No. But again, this is a counting tool, not necessarily a rigorous example of charge like we've seen in the past with Lewis structures or resonance structures. All right, let's look in detail at an oxidation reduction reaction to figure out what species is being oxidized, what's being reduced, and then how many electrons are being transferred. We'll consider this fairly complicated example where we have elemental bromine, so Br2, in aqueous solution. One of our other reactants is sodium sulfite, Na2SO3, which is dissolved in water as well. In this case, liquid water is going to be one of our reactants also. On the product side, I produce 2 moles of sodium bromide and then sulfuric acid, which is dissolved in water. The way we're going to track oxidation and reduction is to get all the way to the net ionic equation, and then it will be a little bit easier to see which reactant's being oxidized, which is reduced, and how many electrons are transferred. So the first thing we're going to do is to form our total ionic equation. So in doing this, we're going to remember that species that are dissolved in water that are ionic will separate into ions. So let's first consider bromine. Now, bromine is not ionic. It's a molecular element, so it exists as molecules, but it's still an element. So no ions are going to be formed there, so that'll remain intact. Sodium sulfite is an ionic compound, so that will separate. H2O participates as a pure liquid, so no ions would form there. On the product side, sodium bromide is an ionic compound. It's dissolved. It's an aqueous solution. Sulfuric acid will form ions as well, and that's aqueous, so that one we would separate. So let's go ahead and write the total ionic equation. I see my Br2 remaining intact. The sodium sulfite separates into sodium ions and sulfite ions. Notice that in sodium sulfite, I need 2 sodiums to bond to each sulfite ion. So the 2 is a subscript in the compound, but once those ionic bonds are broken in aqueous solution, there's nothing holding the sodiums together, so they would appear with a 2 out front. Now, sulfite is one of our polyatomic ions. Remember that those are bonded internally with covalent bonds. Covalent bonds do not break in aqueous solution, so that's going to remain intact. How do we know the charge is -2? Well, the charge on sodium is a +1 based on where it sits in the periodic table. There's 2 of them, so to balance the 2 positive charges of the sodium ions, I need sulfite to be a -2. H2O obviously doesn't change, so that's going to come straight through. Sodium bromide, I'll have from my 2 moles of sodium bromide, I'll have my individual sodium and bromide ions. And then from H2SO4, I'll get 2H plus, and I'll get my sulfate ion on this side. Now remember, H plus doesn't actually exist in aqueous solution. However, it is convenient for us to track reactions that way. So you'll see us sometimes go ahead and write that in a chemical equation, even though we know that H plus by itself doesn't exist, but it actually exists in water as H3O plus. Now let's figure out which of these species is a spectator ion so that we can form our net ionic equation. Let's look at bromine first. Now I have elemental bromine over here, but on the other side is Br minus, so clearly that's not a spectator ion. Let's look at sodium. Well, sodium is on both sides the same, so that would be a spectator ion. Now what about sulfite? Well, it's SO3 2 minus, sulfite over here, but sulfate over here, so clearly that changes. H2O appears here, but as H plus on the other side, so those two would not be considered as spectator ions. So really the only ones we're going to get rid of in the net ionic equation would be these two sodium ions right there. So let's go ahead and form the net ionic equation. So I have the Br2 plus the sulfite plus the H2O, giving the 2Br minus, 2H plus, and sulfate. So there's my net ionic equation. At this point, I want to figure out which reactant is being oxidized, which is being reduced. The Br2 is present as an element over here, so that's a charge of 0. On the other side, Br appears as the ion, a -1, but there's 2 of them. So I know that bromine is being reduced. I'm going from a charge of 0 on the reactant side to -1 on the product side. So 2 electrons transferred. So there's my reduction. Now oxidation. Let's take a look at sulfite. Notice that I have SO3 2 minus here and SO4 2 minus over there. Now what that means is oxidation has occurred because I have more oxygen atoms bonded to sulfur on the right hand side. So there's oxidation. So I can identify what's been oxidized, what's been reduced that way. Now let's see how many electrons are involved. I said that bromine is an element on the left and a minus charge with 2 of them on the right. So that's a 2 electron transfer. So the reduction involves 2 electrons gained. Now it's less obvious how many electrons are transferred in the oxidation. Let's take a look at that. To do that, I need to find the oxidation number of sulfur when it's in the sulfite ion on this side versus when it's in the sulfate ion on that side. So that's how oxidation numbers will be helpful to us. So let's first find the oxidation number of the sulfur in sulfite SO3 2 minus. Now we're going to assign S, the oxidation number X. There's 1 of them. Oxygen is -2 according to our rules. There's 3 oxygen atoms, so that times -2 is -6. The total charge is a -2, so I know that X minus 6 has got to equal -2. Solve for X, and X is +4. So that means in SO3 2 minus, sulfur has an oxidation number of +4. Let's do the same thing for the sulfate species. Oxidation number of sulfur and sulfate we'll assign as X. There's 1 sulfur atom. Oxygen's a -2, there's 4 of them, so there's a -8 contribution. The overall charge is -2, so X -8 needs to be a -2, meaning X is a +6, or sulfur in the sulfate ion is going to have an oxidation number of +2. So now we see that oxidation indeed involves the sulfite. I have an increase in the oxidation state of sulfur from +4 to +6. That's 2 electrons lost, which matches our 2 electrons gained. So that's an example of how we can use the net ionic equation to identify what's being reduced, what's being oxidized, and then how we would use oxidation numbers to see how many electrons are involved in the total transfer.